Welcome to this MCA webinar on designing an optimal rotary motion joint for robotics and factory automation, presented to you today by Harmonic Drive. This webinar will be recorded, and an email with a link to the recording will be sent to you within the next 24 hours. If you have any questions on the presentation material, please feel free to submit questions via the panel on your right, and they will be answered as time permits. You may also contact the speaker directly after the webinar. My name is Kathleen Straight with MCA, and I'm joined by our presenter today, Bob Mullins. Bob Mullins has been with Harmonic Drive for 23 years and is currently the Vice President of Sales. Bob started in a field sales as a sales engineer in the Midwest, and for the past 9 years has held a management role at the company's headquarters in the Boston area. Through this period of time, Bob has been involved in numerous customer applications and projects in the field of motion control. He received his Bachelor of Science in Mechanical Engineering from the University of Connecticut and his MBA from Illinois Benedictine University. I would also like to thank our two sponsors today. Electromate is the exclusive Canadian distributor for Harmonic Drive and specializes in high-performance robotic and mechatronic systems, including servo and stepper motion solutions, positioning actuators, and robots. Electromate's extensive product selection is backed up by just-in-time delivery and stocked inventory. Electromate offers engineering assistance and technical support by their dedicated customer service team. I'd also like to thank Harmonic Drive. Harmonic Drive designs and manufactures precision Harmonic Drive servo actuators, gear heads, and gear component sets. They work with customers of all sizes to provide both standard and custom engineered products. Harmonic Drive provides high precision, high performance solutions to meet the requirements of the customer's mission-critical applications. With over 50 years of experience, their expert engineering and production teams continually develop enabling technologies for the evolving motion control market. And with that, I think we'll get started. Take it away, Bob.
Thank you, Kathleen. Welcome to a Harmonic Drive webinar done in cooperation with Electromate and MCA about rotary joints for robotics and factory automation. My name is Bob Mullins, and I would like to welcome everyone. Thank you for taking the time to join us today. We will start this webinar with an introduction to harmonic gearing. This should help those that may not be familiar with the product and perhaps act as a refresher for those that are. We'll cover harmonic gearing principles in operation and also performance and ratings. Following the harmonic gear introduction, we'll delve into the reasons why to use gear components versus gear heads versus a complete actuator. Lastly, we'll focus on rotary motion joint design using harmonic gearing. Here we'll look at and comment upon design examples of various rotary motion joint designs. The objective of this presentation is to hopefully give everyone in the audience at least a general understanding of harmonic gearing and rotary motion joint design. We will not be spending much time talking about our various Harmonic Drive products, but only as necessary to give enough background to understand the design examples. First, just to clarify, what is Harmonic Drive? Harmonic Drive is a trademark and also the name of our company. When the Harmonic Drive gear was originally invented in the 1950s, it was referred to as strain wave gearing, which is still applicable today. However, in that strain wave gearing is not a common term in use today. In this presentation, I'll be referring to our gearing as harmonic gearing or gears. Let's talk about the harmonic gear construction. Shown here is a harmonic gear which consists of only 3 basic elements. The wave generator is a special thin race bearing. The Flexspline is in the form of a cup and has external gear teeth. The third element is the circular spline, which has internal gear teeth. Just a little bit more about terminology. As mentioned, the Flexspline in this depiction is in the shape of a cup, and therefore this gear form can be referred to as a cup type. Also, as we talk further today, I may use the words gear set or component set. These two terms can be used interchangeably as they have the same meaning. Gear set or component sets are words to describe the entire group of harmonic gear elements, the wave generator, the Flexspline, and the circular spline as shown here. As you can see, it's a fairly simple gear system in terms of number of parts. From this comes extreme reliability. The harmonic gear is also very lightweight, and in terms of torque to weight ratio, it's an optimal gear system and a key reason why you'll find it being used extensively in robotic arms. Any weight added to a robotic arm only detracts from the payload capability and speed. It is a lightweight combined with precision, zero backlash, and unique form factors, including through-hole designs, that make harmonic gearing ideally suited to robotics. Now let's look at each of the three basic gear elements in more detail. The wave generator is a thin bearing fitted onto an elliptical hub. It generally is mounted onto the input shaft or motor shaft. As the hub is rotated, a pair of moving waves is produced on the outside of the non-rotating outer race of the bearing. This slide calls the wave generator an assembly, which includes the bearing plug and an Oldham coupling as shown. Generally, we refer to the entire assembly as simply a wave generator for short. The Flexspline is in the form of a round steel cup. It is thin-walled, it is radially compliant, yet torsionally stiff. It has gear teeth on the rim of the cup. When the wave generator is inserted into the bore of the Flexspline, the rim conforms to the elliptoidal shape of the wave generator. As the wave generator plug rotates, its major axis creates a pair of moving waves on the Flexspline rim. The circular spline is a rigid ring with internal teeth. It engages the teeth of the Flexspline along the major axis of the wave generator ellipse. The circular spline has two more teeth than the Flexspline and is generally fixed and mounted within a gear housing. At the major axis of the wave generator ellipse, gear engagement is created as depicted in the diagram at the right. The blue is the wave generator, the black is the Flexspline, and the red is the circular spline. With today's harmonic gearing, approximately 30% of the total number of teeth are engaged simultaneously. As already mentioned, the wave generator is normally the input. What hasn't been said to this point is what is the output? Well, it can be either the Flexspline or the circular spline. Normally, the circular spline is fixed with the Flexspline acting as the output, but it is also possible to fix the Flexspline and take the output off the circular spline. To explain how a harmonic gear operates is difficult. In this case, certainly a video is worth 1,000 words or pictures. Let's view the three elements and then a harmonic gear in motion. The wave generator is an anti-friction bearing, and its purpose is not to handle loading external to the gear, but to slowly create a pair of waves on the OD of the bearing. The Flexspline with external teeth, the circular spline with internal teeth, the wave generator offers low friction, creating a pair of moving waves which cause gear motion and engagement. The Flexspline may appear to have discontinuous motion, but the output is a sum of all motions and ends up being very smooth. You'll note the teeth when engaging move in a radial direction, and unlike involute motion, teeth do not wear and the zero backlash is not compromised. Now that you've seen the basic gear motion in operation and the gear reduction in action, let's talk more about gear reduction ratios. Harmonic gearing inherently has high reduction ratios. It is in line and offers high reduction ratios in a single stage, whereas other gear systems typically require multiple stages at the expense of size, weight, and precision. Ratios offered are as low as 30:1 and up to 160:1 or even higher. Gear ratio is determined by the number of gear teeth. For a given size harmonic gear, many ratios are offered. Geometry and weight of the component set is independent of ratio. In other words, changing the ratio does not change the size of the gear nor weight. It's simply a matter of cutting different number of teeth in the Flexspline and circular spline. So how are the various ratios achieved? By simply changing the number of gear teeth. And how is the gear reduction ratio calculated? First, as stated earlier, the circular spline has 2 more teeth than the Flexspline. It is a 2-tooth difference compared to the number of teeth that creates the ratio. For Flexspline output, the gear reduction ratio is obtained by the Flexspline moving the 2-tooth difference for every wave generator revolution. In this example, the ratio is 100:1, and you can see how the ratio is calculated with a Flexspline having 200 teeth and the circular spline having 202 teeth. With the Flexspline output, direction of rotation is opposite to that of the input. Although it's more conventional to use the Flexspline as the output, the circular spline can be the output, providing the Flexspline is fixed. Based upon convention, all of Harmonic Drive tabulated ratios are based upon Flexspline output. In the case of circular spline output, it is very easy to figure the ratio. Simply take the Flexspline ratio and add 1. If the Flexspline output is 100:1, taking the output off the circular spline will be 101:1. Or in the case of 80 or 120, circular spline output would be 81:1 and 121:1, and so on. The calculation is also shown. The calculated result is a positive number for circular spline output, and this reflects the output rotating in the same direction as the input. Harmonic Drive gearing inherently has high reduction ratios and provides a means to realize high torque multiplication from the input side to the output side. Since the gearing is lightweight, torque can be amplified without greatly adding to the weight to the system. Besides high reduction ratio, which is typically needed in robotics, another common requirement is zero backlash. Zero backlash assists with precise positioning and quick settling times. Zero backlash happens to be inherent to harmonic gearing. Other gear types cannot run with zero backlash without compromising performance or life. Teeth are engaged on both sides of the tooth flank, and over time there is no backlash creep. The gear teeth do not wear due to the unique gear tooth motion. The teeth engage and retract radially and more or less walk over each other without sliding contact. With permanent zero backlash, high performance is maintained. No adjustments to the gearing nor adjustments to the software for tuning are needed. Due to zero backlash and having multiple teeth in the engagement, there is also very low loss motion. Harmonic Drive gearing has very good positional accuracy, on the order of less than 1 arc minute. As a result, output velocity ripple, which is a function of positional error, is very smooth. This comes as a result of not only very low tooth-to-tooth error, but also from the torque being distributed simultaneously over many gear teeth. In terms of a robot arm, the smooth motion of the gearing allows for tight motion control and accurate positioning or tracing when in motion. Just a quick note on lubrication. Either grease or oil is suitable. Harmonic gearing is not extremely sensitive to lubricant selection like, for instance, worm gearing. However, to obtain the best performance along with achieving long lubricant life, we offer factory greases we call SK1, SK2, and 4B number 2. In addition, special greases can be selected for extreme environments such as vacuum, low temperature, and space flight applications. Gear materials can be adjusted for the application, but normally for robotics and factory automation, standard materials are utilized. Some of the material and coating options are shown here. We can offer product in stainless. The gearing or output bearing, I should say, can be black chrome for corrosion protection. I have commonly put phosphate coating on gear housings. Special bearing separators, either phenolic or brass, can be used for wide temperature ranges. The products can be lightened, and also we've done special cleaning in the past for applications, for instance, like in vacuum. Let's talk about the Harmonic Drive performance and ratings. Due to its unique construction versus other gear types, harmonic gearing has torque ratings that are specific to itself, and so it's probably worth going into some detail here. Rated torque is what we use to calculate fatigue life. It relates to the wave generator bearing. At full rated torque and rated speed, for the CSG product, the L10 rating is 10,000 hours, or 5 times that for average life. There's also repeated peak torque. This typically relates to motion profiles having accel or deceleration. During these portions of a move profile, the repeated peak torque should not be exceeded. The gearing can withstand unlimited number of cycles up to this torque load. Lastly, momentary peak is the maximum recommended torque level the gear should see, and it's based upon Flexspline strength. Although it continually flexes, the Flexspline is not the life-determining element of the harmonic gearing. Again, it's the wave generator bearing. Neither is tooth wear a concern. Flexspline tooth wear is virtually non-existent over the life of the gear, and therefore the zero backlash is permanent within the harmonic gearing. In operation, the Flexspline is designed for infinite fatigue life. The flexing action induces stresses in the material well below the endurance limit of the steel, as shown here. Let's consider how the Harmonic Drive gear ratings compare to the SN curve. Roughly speaking, we can display the relation of various torque ratings. If rated torque is assigned a reference value of 1, then repeated peak torque would be about 2. And momentary peak torque would be 4 times that of rated. In relation to the SN curve, you can see that the momentary peak is just below it with some factor of safety. Going yet beyond, we encounter ratchet torque at about 8 times rated. Ratchet torque can occur at this load level and only when there is rotation. It will not happen in a static condition. At the ratchet torque level, the Flexspline distorts, with the result being a movement, causing in effect a jumping of teeth, with the Flexspline ending up no longer being concentric relative to the circular spline. This is an undesirable situation which will eventually lead to Flexspline failure, at least potentially. In a static mode, with a large torque being applied to the output with the input held, a torque of almost 17 times is required for buckling before buckling occurs. Obviously, the result is a catastrophic failure. Harmonic gearing, although having fine teeth, is a very durable product. Modes of failure don't include tooth breakage or shearing. Virtually the only modes of failure relative to the Flexspline from overload are either ratcheting or buckling, as depicted here against the SN curve. Wave generator bearing life is shown here as well. My computer's acting a little slow, so what's shown here is the infinite fatigue life, which is below the SN curve, and over on the left, in the reddish area, is the finite fatigue life. So in actuality, for a limited number of wave generator revolutions, the Flexspline can actually be operated above the momentary peak torque limit. But in general, we do not recommend doing so. Reliability is of extreme concern with space satellites, and is one reason harmonic gearing is used on virtually every satellite in orbit. As already mentioned, the wave generator bearing is a determining factor when it comes to fatigue life. At rated torque, mean time between failure is 45,000 hours, and at 50% of rated torque, it's significantly more, at 360,000 hours. Next, let's look at and consider torsional stiffness of the harmonic gear. Torsional stiffness is a function that is predominantly determined by the diameter of the gear. Increasing the diameter of the gear correlates to increased stiffness. Output position is determined by the accuracy of the gear, and when under load, by also the output compliance, which can be estimated. Shown as a torque deflection curve for harmonic gearing. It is simulated by 3 spring or K factors. Essentially, the gearing becomes more torsionally rigid as the torque load increases. The K factors are in our catalog and can be used to predict estimated torsional windup under torque load. This is a typical accuracy trace from an in-house test stand. The y-axis relates to positional error, and the x-axis is input revolutions. In this case, it represents 1 rev of the input. To measure the positional error, the input rotates, and it's compared against output position with encoders. The difference from theoretical output position is recorded as shown. The positional error has a frequency signature, but of very low magnitude. The predominant frequency is twice the input speed. Many of our customers rely upon high accuracy provided by Harmonic Drive gearing. Our catalog states 1 arc minute max for most gearing. However, typical ship product is much better, as in the case of this unit, which measured less than 1/2 arc minute or less than 30 arc seconds. We typically say repeatability is less than 15% of accuracy, or plus or minus 5 arc seconds. Repeatability can be measured as shown, but essentially we are referring to approaching a set position from one direction over multiple occurrences, and we measure the difference in the final position between those occurrences. Repeatability is often an important consideration in robotics and factory automation. In these kinds of applications, making repetitive moves is typical, and the machine or robot builder will typically be looking to optimize repeatability. Benefits versus other gearing. The benefits of harmonic gearing are numerous, but what's interesting is that all of the characteristics listed are desirable in the field of robotics. This explains why harmonic gearing is so widely used in the field. There's zero backlash, high positional accuracy, repeatability, compactness and lightweight, or high torque to weight and high torque to size, concentric design, design flexibility, and this is something that is perhaps not so outwardly apparent and will be giving focus in the later part of this presentation. There is extreme reliability, and there's an internally balanced torque couple which helps minimize the size of the supporting structure. That completes our discussion on harmonic gearing performance and ratings. The next section of this presentation concerns factors involved with deciding whether to use a component gear set, a gearhead, or an actuator. There are a wide variety of rotary motion applications in robotics and factory automation. We'll be only able to present a few given our time constraints, and we'll be focused more towards industrial automation than consumer, space vehicles, or medical applications. By the way, the medical industry is increasingly using robotics such as in surgery, in hospital deliveries, physical assist devices such as exoskeletons, and also in rehab. Shown on the lower right is a wheelchair arm built by Canova, a Canadian company. The application will allow people with limited or no use of arms to eat independently and to pick up a variety of objects. The robot arm is lightweight, relatively low cost, but yet highly functional. We expect the medical community to increasingly use robots, and this is just one example. Okay, what are some of the basic considerations for a rotary motion joint design? Some may seem obvious, but it's important to recognize that any rotary motion joint design used in automation starts with these basic considerations. First, there's performance, speed, payload, reach. These factors are basic design criteria for a robot. Lightweight is very important and affects the performance elements of the robot. For instance, reduced weight at the end effector results in higher allowable speed at the base axis. Additionally, there is positioning accuracy and repeatability. This shows a basic concept. Left shows good repeatability, but away from the target. Right shows tight dispersion and around the target, which is desirable outcome. Environment. Type of electrical power available. For instance, mobile robots are typically limited in voltage to either 24, 48, or 72 volts. Safety is obviously important, and a separate subject matter by itself. The rotary joint will need to be able, whatever is thrown at it, in terms of temperature, contamination, and possible abuse. And then there is cost. Of course, cost is always a major consideration. Quite often there are trade-offs to be considered in terms of cost and performance. Harmonic gearing is available as a component set. Most often in robotics, component gearing is selected. Less so in factory automation, where gearheads or actuators are more typically deployed. Why is basic gearing oftentimes used in robotics? By utilizing component gearing, the designer can utilize the machine structure, a robot arm structure, to install the gear. This gets dual use out of the machine structure and can serve to minimize weight and size and reduce overall part count. So it's primarily weight that is the driving factor to using gear components. Other reasons to use gearing may revolve around the optimization of the output bearing selection for what's required of the joint. Also, gearing, due to various form factors, lends itself to design flexibility and creative solutions to tight situations. Using component gearing, though, doesn't come without some negatives. It requires design resources, precision parts and assembly, testing, reliability studies, inspection, purchasing of parts and parts inventory. Much of this can be eliminated by choosing a gearhead. Gearheads are more complete and by definition include an output bearing. Actuators are one step up from gearheads in terms of integration. They provide a means to have a drop-in complete rotary joint. As we just spoke about, we can consider gearing, gearheads, and actuators as potential solutions. Component gearing is a basic building block leading to gearhead and actuator products. If one understands the three basic gear set types, it will provide an insight into the higher level products. Also, if a designer can envision a gear component being used or selected, the next logical step could be to look for a gearhead or actuator that has already been developed and can fulfill the complete design need. So what are the three basic types? There is a cup type, which we had been referring to and saw in the video. Then there is a silk hat gear set, which is similar but is unique by virtue of having a Flexspline with a brim that looks like a silk hat. That's the reason why this gear type is referred to as silk hat. By having the brim to attach to, the left open is a large through hole. Normally silk hat gear sets are selected for this reason. Finally, we have pancake gearing, which has been available for many years. Today it's our value product. It doesn't offer the level of performance offered by cup or silk hat gears, but can meet many application needs where true zero backlash is not required. Here shown is a silk hat gear set, and later on several of our design examples will incorporate this product. When the silk hat gear on the left is used in a unit type or a gearhead with a cross roller bearing, which is shown on the right, the Flexspline ends up being attached to the outer race, and the circular spline is attached to the inner race. The input is the wave generator, and in this case, on the left side of the wave generator, there are holes to attach, let's say, an input pulley. There are another set of holes shown on the top section in the cross roller bearing for fixing the unit. So mounting holes in the outer race of the cross roller bearing, and there are mounting holes in the inner race of the cross roller bearing. Either one of those races can be used as an output. This diagram shows a generic installation of a harmonic gear cup. You can see there are a number of design guidelines that need to be followed. What is important is that all three gear elements are located concentrically and are axially located relative to one another. The mounting is relatively simple, but precision is required, as denoted. And further detail can be seen in our catalogs. With the gearhead, there is much less to be concerned with. Since the component gearing is held in the housing, there is an output bearing aligning the Flexspline. The only area the designer needs to attend to is the input side. Here shown is a common installation with a motor having an adapter plate and the wave generator attached to the motor shaft. From this point, the gearhead and motor assembly are brought together with the result being a compact gearhead motor assembly, or effectively a simple rotary joint. In the following series of example joints, we'll start with the SCARE robots, and we'll move into other robot applications, and then finally a few factory automation type applications. Although most of the examples are in robots per se, you can find the same mechanical concepts in factory automation being applied. This is an example of a gearhead product being used in a SCARE robot. The motor extends within the harmonic gear and therefore doesn't extend the length of the assembly any more than it needs to. The wave generator features an Oldham coupling to compensate for run-out error of the motor shaft. The circular spline is located in the upper arm segment and acts as a fixed element. The Flexspline acts as an output element and drives the lower arm segment via the flange of the output bearing. Typically, harmonic gearheads incorporate cross-roller bearings for reasons of compactness and high moment capability. You'll note the cross-roller bearing interrace forms the outer flange, thus eliminating the need for a separate output flange and thus minimizing weight and part count. This particular example is simple from the perspective the designer was able to take advantage of using actuators. This means lower initial costs and being able to use standardized hardware. Larger actuators are used at the base where torque requirements are high and weight is less of a concern. The upper actuator rotates axis 1 and its hollow bore is utilized by the lower actuator. The hollow bore permits extending the output shaft from the lower actuator up through the upper actuator. In the end, the lower actuator drives axis 2 via the extended shaft and pulley arrangement. Smaller actuators with no through holes are located in the area of axis 2 and via belts serve to move axis 3 and 4. Axis 3 is a ball screw nut. When turn moves the ball screw up and down. Axis 4 is a ball spline which rotates the vertical shaft. I imagine this would be useful if a part manipulator were located at the bottom of the shaft, for instance. Note that even the smaller actuators are located away from the end of the arm, thus helping to keep the arm inertia down. In this design, axis 1 or the upper arm segment is directly coupled to the actuator. Axis 1 has the most influence on positional accuracy of the final output, and therefore it makes sense to direct couple it to the arm if possible. Axis 2, on the other hand, is driven by a belt. This permits having lower weight and less arm inertia and facilitating fast speed. Here we use the FHA actuator product in this design. This is an example of a scare robot having motors mounted below and having a short overall height. Scare robots are used for fast assembly tasks. They have high dynamic performance and require gears to be lightweight and have excellent repeatability. This design example shows two axes. The axis on the right is the base axis, or axis 1, and moves the upper arm segment. On the left is axis 2. It uses the same type of gearhead, only slightly smaller for less weight. It moves the lower arm segment. Note, the motor shaft extends well within the bore of the gearing. Here, the designer was able to use a gearhead design to take advantage of the built-in cross-roller bearing. The gearhead is simply bolted into the robot structure, making installation and assembly relatively easy. This is another scare robot design, but perhaps more innovative. The differences are, both motors are located at the base axis, or axis 1, which frees up the weight of axis 2. Axis 1 moves the upper arm segment. Axis 2 moves the lower arm segment. The motor for the second axis has a shaft extending through axis 1, going up to a pulley, and then over to axis 2. By utilizing the through bore feature, the drive belt can be located up within the arm structure. The particular gear style utilized is very compact. The circular spline and cross-roller bearing interrace are integral and not separate pieces. The result is a gear reduction in little more space than required for the bearing alone. The product featured is one of the most compact gearhead or unit type solutions. Hollow shaft designs can be found in both robotics and factory automation. Harmonic drive gearing is rather unique in this regard and can be found therefore in many applications requiring a hollow shaft. In robotics, the hollow shaft is commonly used to run cables. In factory automation, more often the hollow provides a means of providing auxiliary power up to the final workpiece. For example, pneumatics may run up through the actuator to a work-holding clamping device. There are many reasons for hollow shaft designs. Shown is a harmonic drive actuator with similar functionality to a DD drive or direct drive motor, but with 1/10 the weight and much smaller size. Historically, these types of tables would be mechanically driven, such as with a cam indexer, but servo control is becoming more widely accepted and preferred for many applications. Robot shoulder axis. Incorporated is a special low inertia wave generator in this gear for high acceleration, and a special circular spline to facilitate being secured to the robot arm structure. As you may be noticing, quite often the harmonic gear components are customized to suit the particular application. The input shaft in this design goes through the gear set, which permits spreading the ball bearings, thus providing an input shaft that can handle high moment loads that could be induced, for instance, if it were being driven by a tension belt and pulley. An interesting feature of this design is that the input and output are on the same side of the gear reducer. This demonstrates a type of flexibility that can be achieved when using component gearing. Normally we see the input shaft entering into the gearbox on the side nearest the wave generator or on the right. This design has the input shaft entering into the gear from the left or output side. This design example is for a larger assembly used on a base axis of an inverted robot. The design uses a component gear set, and the design has some unique requirements. The input coupling arrangement allows for quick removal of the servo motor. There is a large 4-point bearing to support the entire hanging robot, and an absolute encoder driven via a tooth belt from the output side of the gear is used for position measurement. This arrangement enables the actual output position to be detected even after power failure. In the center, of course, is a harmonic gear. The whole design of this gantry robot axis is built around a standard gear set. The hand axes of gantry robots must be compact and light to reduce the load on the linear axes and to optimize the dynamic performance of the robot. In order to reduce the weight of the hand axes, the motors are usually located outside of the hand assembly. The motor torque is transmitted to the hand via parallel shafts inside the vertical axis cavity of the robot. The corresponding outputs from the two inputs are located as shown. This design example incorporates hollow shaft gearing and solid input shaft gearing. The first hand axis is driven via a spur gear arrangement. The second hand axis is driven via a bevel gear arrangement. The drive shaft for this axis passes through the hollow shaft area of the gear set above. The second axis gear features a special output flange that is in an ISO configuration. This allows easy connection to a variety of gripper and tools. The design example shows that both flanges of the SHF units can be used as a fixed element or an output element. The first axis gear uses the flange attached to the Flexspline as the output element, while the second axis uses the flange of the circular spline as an output. Here is another variation of a hand axis. Shown would be the fifth and sixth axis of a robot. The fifth axis incorporates a CSF2UH unit with a special hollow shaft design, while the 6-axis features a similar type unit, but with an input shaft. Both gears are driven via tooth belts from motors located within the preceding arm segment of the robot. The drive shaft to the 6-axis passes through the hollow shaft. Power to the 6-axis is then transferred by a belt configured in a right angle. For the gear on the left, or for axis 1, the wave generator is supported by one bearing located in a specially modified output side clamping ring and another located in the input side flange. For the gear on the right, for axis 2, the shaft passes through the unit and is supported by bearings located in the input side pulley and output side flange, respectively. Both gear units have specially designed output bearings to support high tilting moments. Turntables. This is another area in factory automation. On the left is a special turntable for an optical measuring machine. It utilizes a custom gear head with a 4-point bearing. The ball bearing has less friction than a cross roller, thus permitting freer movement of the output when micro-stepping. This helps facilitate the extra fine positioning control. Typically, when stepper motors are used, we do not use an Oldham coupling. Shown here is a wave generator hard coupled to the motor shaft. On the right is a rather unique design for machine tool turntable. It uses a CSD component gear set, which is the thinnest available gear product. A gear head was not selected because the requirements are rather specific to the application. The table is supported by needle roller bearings for high load capacity, stiffness, and compactness. The table is fitted with a brake. A very stiff brake is added to fully secure the workpiece when the machine tool is cutting. The input is a pulley, which helps keep the overall height of the assembly to a minimum. Shown is a tool revolver or tool holder. It needs high repeatability, and the spec is plus or minus 5 arc seconds. The input is a pulley, and as in the early example, the motor is offset and not shown. What is especially notable about this application is the encoder, which is attached to the output, but located on the input side of the gear reducer. A thin shaft runs through the center of the harmonic gear to make the connection. Included is a customized wave generator having support bearings for a pulley, Delta robots. Delta robots require different performance than an articulated arm or SCARA robot. They operate at faster acceleration rates and typically are moving much lighter weight objects. Consequently, acceleration rates can be limited by the prime movers themselves, the servo motor and gearing. Therefore, low inertia servo motors together with low inertia gearing is needed for rapidly moving arm linkages, such as required for ultra-fast pick-and-place applications. The calculation to determine gear loading can be complex. Our company has created simulation software that takes into account the varying load inertia from the actuator, gear, upper shaft, upper arm rod, and tool center point. The simulation software can be used to size the gearing and also simulate the Delta robot performance. Custom harmonic planetary gear heads have been used in this application, having very low input inertias. Also, if an end effector is utilized, it also needs to be very lightweight. Harmonic Drive FHA mini actuators have been utilized here. Most often our customers think of harmonic gearing as high precision and high reliability. Naturally, associated is also a cost premium. However, in reality, harmonic gearing is typically no more costly than other precision gear types. In actuality, the design flexibility offered by harmonic gearing oftentimes makes precision applications more affordable than otherwise. And when it comes to meeting tight cost targets, there are options. On the left is a Scare robot having an off-the-shelf servo motor combined with a planetary gear. It uses our recently introduced product addition, the HPN Planetary, which offers a high value along with high quality. Where lower cost component gearing is needed, pancake components can oftentimes be selected. Although not being true zero backlash, this product is available in low backlash versions and has performance suitable for robotics. Shown is a typical pancake gear installation. Both of these configurations have been used in lower cost robot arms. This is the last application example I'll show, and I left basically the best for last. I think it's a thought-provoking design, and it demonstrates what can be accomplished with harmonic drive gearing while using creativity. I won't go into great detail, and we'll leave it to you if you'd like to consider it further, if you like. Essentially, though, what is shown is a single motor connected to two harmonic gears. The result of this design are two coaxial outputs, each rotating in the output direction, in opposite directions. The highlighted ratio selected in the table shows them rotating at the same speed relative to each other. Different relative speeds between the two outputs can be attained as shown in the table. This is a rather unique design, and if you care to download the presentation afterwards, I think it might be considered a brain teaser in a way. So in summary, precise rotary motion is required for today's increasingly demanding application in robotics and factory automation. This presentation demonstrated many of the reasons for using harmonic gearing in precision rotary joints and the level of design flexibility that can be realized. We are here to support all of you in your design endeavors and are eager to assist you with your next precision rotary motion challenge. Thank you, and that completes my presentation today. If there are any questions, be happy to try and answer those.
We have a few questions, Bob. Let me just start with, can other than catalog ratios be offered?
Yes. Harmonic drive gear of any particular size can be made with a numerous number of ratios, and all we have to do is change the number of gear teeth to get different ratios. What might be required is special cutters, for instance, to create a different number of teeth. But this is something that we can do for our customers if they have a specific ratio that's required.
Okay. What is the connection between HD Systems Japan, HDAG, and HD LLC?
Interesting question. All three companies are associated with other. We tend to think of ourselves as one family. Harmonic Drive Systems in Japan is the largest facility, and they are the parent company of our company here in the United States, Harmonic Drive LLC. Also, we have an affiliate company in Germany, and that's Harmonic Drive AG. All three companies work very closely together to advance the harmonic drive gear technology, gearhead technology, and actuator technologies.
Okay. Does Harmonic Drive charge for NRE when doing customizations?
I would say maybe 75% of our products that we offer to customers are customized in one way or another. And normally we do not charge for NRE. It's just part of our business. NRE would only be applicable if it was really extensive project.
Okay. Let's see. Can harmonic drive gears be further lightened on a custom basis, and what are the considerations?
They can be, yes. What happens when we lighten them, we'll typically take out material, which will decrease the strength of the product. So there is some trade-off there, and we need to be careful not to compromise the gear excessively. And how much material we can take out is dependent upon the loads in the application. And we can work with customers to optimize the product in this regard.
Okay. Can harmonic gear characteristics such as starting torque be adjusted for an application?
They can, yes. For instance, starting torque, we can build the product with, for instance, low starting torque as an objective, and we can control and measure that starting torque to verify it's maybe lower than standard, for instance. And there are other characteristics of the gear that can be optimized for particular applications.
Okay.
Namely stiffness, back driving torque, are just a couple others to mention.
Can you test a specific product prior to shipment?
Actually, we do test product prior to shipment, and we can provide test data relative to positioning accuracy, loss motion, starting torque, and some other characteristics as requested.
Structurally, how did Harmonic Drive reduce the weight of the recently introduced lightweight series?
The recently introduced lightweight series has an aluminum structure to it, and all of our products up to this point have been completely made from steel. The aluminum structure, what we do is we have a metal insert in the aluminum structure for the circular spline gear teeth, and therefore we have a hard surface, but we still have, and we have the aluminum structure for lightweight.
Okay. I think we have time for one more question. We've got some, can you come to our facility to present harmonic gearing to our engineers who may not be familiar with the product and tell us how it can be applied?
I'm sure any of our regional sales engineers would be more than happy to visit and help people with their applications. We regularly do lunch and learns, and we have sales offices on the West Coast in San Jose. We have an office in Chicago and also an office in Hauppauge, New York, to cover the East Coast. As well, we have Electromate, our exclusive distributor in Canada, covering most of the provinces.
Great. Okay, I think that wraps up our webinar for today. I want to thank you, Bob, for this very informative webinar, and thank all of the participants today, as well as our sponsors, Electromate and Harmonic Drive. And I just want to remind all the participants that the webinar has been recorded, and we will send an email with a link to the recording within about 24 hours. Again, the contact information is up there for Bob. If you have any further questions on the presentation material, you can contact him directly. And just be sure to check out our website, motioncontrolonline.org, for a list of any of our other upcoming webinars. Thanks, everyone. Have a great day.
Thank you.